So I think you have heard a bit this week that topological recursion is counting surfaces. And I don't know if you had, maybe Elba gave a motivation from 2D quantum gravity, I'm not sure. So if I'm repeating something you already heard, please stop me. But I want to remind a bit how in physics this came, and quickly, I'm going to transform that into a math problem. So this originated from 2D quantum gravity. So what is gravity? You want to consider a theory where your observable R is the metric structure of your ambient space. And because we're in dimension 2, so you will take a certain surface and you want to look at metrics. And well, you also want some symmetries. So you're going to look at metrics up to conformal transformations. And up to diffeomorphisms. Am I writing big enough or not? It's okay. Yeah, so complaints are very welcome. I may not reply to them, but you can complain. I'm very happy to hear. Good. And so this is just about gravity. But quantum means that, in fact, what is realized in nature is not a fixed metric, but more like a fluctuating metric. It's even more complicated because you would like to do a sum over all possible metrics and their evolution with a complex weight. But to simplify a little, quantum, you could say it means that you have actually a certain probability measure on that space. So you look at random metric for a certain probability measure, and there's various choices you can try to do on this. And then you're asking questions, for example, what is the behavior, what's the length of that curve on the surface, in expectation, what are the moments of this. So you want to know information about random geometry. So it means that you're going to compute normally integrals over the space of metrics. And so that's essentially what mathematicians, so that's in physics. And that's one version of the problem for mathematicians, is that you're going to, counting surface for us is going to mean compute integrals on the space. And so this surface, I will assume it's oriented and connected, so it's going to have some genus and a certain number of punctures or boundaries. And so essentially what we want to do is to compute integrals over this space, which is called MGN. What that has to do with the actual problem of quantum gravity, well, in mathematics, a bit of the physics precision is, precision or imprecision is lost. So we're just going to replace this by this problem. If you want really to hear about 2D quantum gravity in physics, and there's many interesting developments even now, I think Bertrand and François David are the right person to ask. Good. So more precisely, this MGN, so it turns out that by Riemann uniformization, this is the same as the set of Riemann surfaces, so complex structures on surfaces. So I'm going to fix, so a point here is a class, an equivalence class of objects like this, where you have a curve, compact connected curve, smooth of genus G, and a certain number of marked points. So maybe I write P1, Pn, but I want to say that this P is a map from the integer segment. It's an embedding of the integer segment into C. And you want to look at this up to isomorphism. So by holomorphic map, respecting the punctures which are labeled. Okay, so let's see an example of points, or actually a family of points in this space. So n for me is the integer segment 1. And this is just a fancy way to say that I want my points to be distinct. Okay. So an example. You can consider a family of elliptic curves. So I'm going to look at this family. So the set of points in C squared with coordinates x and y, and t is here a fixed parameter. And I remove 0 and 1. And this you can compactify by adding the points at infinity. And this is for t different from 0 and 1. This is an elliptic curve. So topologically, this is a torus. And what is happening for t goes to 0 or t goes to 1? Well, you see the equation, there is a square here. For example, let's say t equal to 1. I'm going to have x minus 1 squared. And so locally, when you zoom around the point of coordinate x goes to 1, what you see is something that behaves like this. So you have two components meeting, so it means that actually you have a node. So the surface here is rather going to look like this. So it's not anymore a torus, so it's a pinch torus. And so that ET, if I look at the isomorphism class of this, it is a point in, so it's a curve of genus 1. And I'm going to equip it with the point P of coordinate 0, 0. And so that's a point in M1, 1. So points in this space are actually curves, or rather isomorphism class of curves, but very often you work with representatives.
Sorry. Can you write a bit
Yes. Here? Everything? And there's another thing that we can notice is that for this curve, there is an automorphism. So again, if t is different from 0 and 1, actually the automorphism group is 0 to z, because you have a holomorphic involution which is sending xy to x minus y. Satisfy the same equation. And so this example illustrates all the little issue one has when one wants to make sense of integrating over MGN. So there's two issues. Is first that curves, so when I will say curve, it will mean complex curve, but of course it corresponds to a surface in the real world. So curve in general, so they can have automorphism. So what does it mean to count a curve when you have automorphism? Well, you say, well, if there's finitely many automorphisms, you should divide by the number of automorphisms. That's the right way to count. So when there are finitely many automorphisms, this can be circumvented by dividing by the symmetry factor. But this only happens when 2g minus 2 plus n is positive. So this is minus the Euler characteristic on the surface. In all the other cases, when you have infinitely many automorphisms, So that would correspond to the sphere, the torus but without a mark point, the sphere with one mark point, the sphere with two mark points. So on the sphere, for example, you know that group of bi-holomorphic maps from the sphere to itself, it's PSL2C. So it's something of dimension 3. If you fix 1 point, it's still something of dimension 2. If you fix 2 points, something of dimension 1. If you fix 3 points, so 2g minus 2 plus n, this is 0, 3, so that makes 1, so this is positive. In that case, you cut down, I mean, naively, the stabilizer to something to the dimension 0, which means it should be points. That's why you have finitely many. So these things won't behave well. If we want to compute integral over the space of sphere with 1 point, it won't behave well because what do we mean? We have to account for automorphism and infinitely many. So I will always assume this. And then that space becomes, it's not a manifold, but it's an orbifold. And so integrating over orbifold, it's not too hard compared to integrating over manifolds. But there's another issue, which is the space is not compact. So you could say, well, it doesn't matter on Rn, the space is not compact, but we know very well how to integrate functions. But typically what you do is either you assume some decay at infinity, or I mean, when you do cohomology, you can do that over compact support. But what we want to do, I mean, you see, we would like to integrate this kind of locus, which is quite natural. But this one, we see that when t goes to 0, 1, we pinch, so we go out of the space. Essentially, this is related to the fact we can go in non-compact directions. So here the thing is that, and I would say natural cycles of integrations, like the one here, the family of this ET, are not compact. So either you really insist to do differential geometry and you have to consider what is the decay near the non-compact direction, or you're an algebraic geometry, you don't want to do that too much. And I precise I'm not an algebraic geometer, but I can try to learn from what they tell me. And so the idea is that you can try to compactify. And there are various compactification, and which one you choose, then you can integrate differential forms, actually cohomology classes. And secretly, it means that when you look at representatives in terms of differential forms, there must be some decay, some particular decay at infinity, which depend on your compactification. And that is totally swept under the carpet. Once you have this compactification, you don't even talk about anymore about decay. You just use the cohomology ring of this compact space. So for the compactification, there is one which is particularly suited here. It's called, so it was described by Dolin and Mumford in genus 0, and then Knudsen in any genera. So it's called MGN bar. And so what it does, it allows nodes. So this would be the isomorphism class of curves. So before here, these curves were smooth. And here we're going to waive a bit that smoothness assumption because a node is not smooth, not a smooth point. We're going to look at what is called stable curves. So a stable curve, this is a curve where there's finitely many nodes. Now these points were locally, so you have two regular functions on the curve, so that locally the equation looks like this. So it's really like this if I draw the real picture. And these nodes should be distinct from the marked points. And we have to put another condition because of the second issue I pointed. Curves can have automorphism. So if you have a node, and here you create a component which is a sphere with two marked points, here you're going to have that curve is going to have a automorphism group of dimension 1. Therefore, it's not finite. Therefore, we won't be able to integrate, again, for the same reason. So stable refers to this condition that each smooth component has Euler characteristic negative, which means I'm in this case, and therefore automorphism of such stable curves is going to be finite. Okay. So by what I mean by component, for example, so here it was a bit simple, but I can add another thing and then with marked points. So that will be the first component, and that will be the second component. I just detach the nodes. That's what I call smooth components. And when you detach the nodes, yes?
What did you count the nodes as?
And that's what I'm going to say now. By Euler characteristics, so this is something with, there's punctures and nodes. So when you detach that, you create two extra points, and it matters to the computation of the Euler characteristic. You include them as marked point of the smooth component, even though they're not marked points on the full surface. And the reason is that when you look at an automorphism of this, some of these surfaces don't talk anymore to each other, because they just pinch, they're independent. And you have this point which sits there, and you cannot move it, because that's what makes it talk to the other. So that's including nodes as marked points of the smooth components. Sorry?
Can you make this example again? I got a bit lost.
So, okay, here let's look at this nodal curve. These are my marked points. And now what the smooth, so you have the normalization, which is this process of taking the smooth components. So here I'm going to have my puncture remain, but I have this part of this half of the node. And on that side, what would you have? So you also detach this thing. Split in two. And now you have two smooth components. One of them has 0 and 3 marked points, and the other as well. Just that the nature of these marked points depends. Here it is because you have 3 nodes, here it's because you have 1 node and 2 punctures.
That operation is changing the genus.
Yes.
Okay.
It just breaks the curve into irreducible components. And then each of them has some genus and a total number of marked points, including nodes. And that's what we use to compute the Euler characteristic of each of the smooth components. Okay. So once you do that, it is proved that this thing is a compact, smooth orbifold over C of dimension over C 3G minus 3 plus N.
Gaëtan?
Yes?
So Paul Norrie is commenting that the arrow should go the other way around for normalization.
Yes, so that was not a morphism between surfaces. That was a process, so a mechanical wriggly arrow. But indeed, if you really look at that curve, you can map it by identifying. It's a quotient map here. So that's a normalization map. The normalization process is to take that and detach it, but it's not a map between curves.
Thank you.
So Paul is right. Good. And orbifold or not, it doesn't matter too much. You can consider then the cohomology ring of MGN bar. The only thing that, because you have orbifolds and thing of symmetry factors, you cannot do it over the integers. You have to do it over the rationals. Of course, you can do it over C if you don't really care, but so we have now this algebra. And this algebra has the cup product, which is, in terms of differential form, the wedge of differential forms. So it's a cohomology algebra. And because the space is compact, orbifold or not, actually, you also have a version of Poincaré duality. So this is also dual to this, equipped with the intersection product of cycles. And when you take here, you have the integral, which is going to take a certain class and give you, so if I mean Q is going to be a rational number. And this is, I mean, you can only integrate top dimensional forms. So whenever you write something like this, if alpha is, I mean, you split alpha in various cohomological degrees, you pick the top degree you integrate, and for the rest, you just set it equal to 0. So that's extended from H top dimension. So the way we count the cohomological degree is come from the real world, so that there's a 2 compared to the complex dimension. So extended by linearity. Okay. So just extended by 0. Integral of a non-top degree form is 0. Okay. So we're going to replace questions of counting surfaces by computing in this algebra and doing integration. Are there any questions so far? Marta? Yes?
What did you denote with U and N?
Oh,
Cup?
This is just the cup
Cup
product
and
and the
intersection. Oh,
intersection
okay,
product.
okay, okay. Thank you.
So, in fact, these algebra, you see there's one for each G and N, but they're not totally independent. They come with actually more structure. So the first structure is that, in fact, there are natural morphisms between these moduli spaces. First, there's the what you call the forgetful morphisms. In fact, there is more structure in the collection of topological spaces given by the MGN bar. And then what I'm going to write is just by passing to cohomology, this algebra inherits the structure. So the forgetful morphism, it takes a curve with a certain genus and n plus 1 marked points and forgets the last marked point. So here there's n plus 1. And you just keep the same structure, but it's just one point. You just forget the information of this point. Okay. So in MGN, that would make total sense. In MGN bar, you have to be a bit careful because you need to do stable curves. So what if you had your curve here, maybe with a certain genus, but in fact, you had a node and this marked point was here. So that wouldn't be allowed. But if I have one more, I don't know, for example, I, which is here, that would be a stable curve. But if I forget about the n plus 1, it's not anymore a stable curve. Because here I would have, when I detach, I have one node and one marked point. A sphere with 2 points that has all the characteristics 0. So this is, when that happens, this is a certain locus, which one denote delta I n plus 1. I will need it later. So what does one do in that case? Well, you forget first the point. You see this thing is not stable. You just contract it to a point. And when you contract it to a point, what do you do with this guy? Well, when you contract everything to a point, now that's not anymore a node. So you just carry the I here. So you contract unstable components. So we do have such a map, but slightly more subtle than forgetting a point because of this. So this maybe I want to keep.
So what if the rational component has 4 points?
If you had more, then forgetting this one, you would still be stable.
Yeah, sure.
So it remains.
Yeah.
So we had the forgetful morphism. And then we have gluing maps. And so also I will not really explain that, but for some people for whom it makes sense, this more or less tells you have a structure of a modular operad on this cohomology algebra. And some operations we're going to describe during these maps later, you can actually normally do that in any modular operator. That kind of structure in terms of operatic, I mean, I don't really know what it corresponds to, but maybe Pedro, you would know. An operation where you just fill in one entry. What kind of augmentation is it? So anyway, this is for people in higher algebras, but what I want to say, I mean, this is much more simple. I have two kinds of map. So let's call beta 1. And the idea of gluing, you just take 2 marked points and you glue them together. You can do that because you're in MGN bar. So you can, when you glue, you get a node. So perhaps I do it in this way, n1 plus 1, n2 plus 1. And here I go to G1 plus G2, n1. My arrow needs to be smaller. Yes, so I'm going to make a drawing. And here you have your stable curve. maybe several components. I'm not doing that anymore. You have the points, 1, 2, etc., and 1, and then you have an extra 1. The number n1 plus 1. Let's write plus 1 to the right for me, the last point I'm going to glue.
Can you repeat what you wrote for the n's on the right-hand side?
N1 plus N2. And
N1
G1 plus G2.
And no plus number.
No, you will see why. So you take two curves. And then you just take the quotient space where you glue those two. So when I glue those two, I'm forming a node. So this one is here. These ones they're numbered, but I'm going to put them after the number n1. And then I would have the image of my 2 points, which are the same, but I just forget that information. So it's a node, but it's not a puncture. Anyway, punctures are not allowed to be at the same position as nodes in my definition. And so that's why we remove 2 points. So when I had n1 plus 1, n2 plus 1, I just have n1 plus n2 marked points at the end.
Can you make the picture a bit bigger?
This one?
On the right, yes.
So maybe I do it that way. So maybe I even write it in this way. So here just relabeling.
Excuse me.
And this one, we just forget the label.
Excuse me. What's the I there? The
I don't have an I.
on
It's
the
one.
beta
Oh,
I. So
beta 1, Roman I, Roman 1, because there's going to be a beta 2.
okay, thank you.
In fact, it's a bit cheating because for each G1 and 1, G2 and 2, you have such a map. So it does depend on G1 and 1, G2 and 2. Good. And then I have another map, which is why taking two components and gluing, you can also take 2 points in the same curve and glue them. In that case, you're going to create a sort of handle, but degenerate. So you would go from mg minus 1 n plus 2, and you're going to get a stable curve with n punctures, and the way it works. So you have still the points. You have 2 points here. And you glue them. And so when you glue them, you should imagine, so if I topologically deform for the drawing, you should imagine this is something like that. Well, that would be your points identified here as a node. And again, I forget that information is not anymore a marked point, it remains a node. And here, because I don't forget any point, if I have a stable curve here, I also get a stable curve here. There's no problem of bad components which have infinitely many automorphisms. Okay. So we have these maps between the spaces mg and bar. And if you go in cohomology, you can pull back by such maps. If in homology, you can push forward. But since we're in this compact situation where the homology and the cohomology are isomorphic, in fact, we're going to be able to use the push forward of these maps. So we're going to have F and beta 1 star, beta 2 star. So cohomology of this product is the tensor product. So we have such maps, G minus 1, n plus 2. So we can relate various cohomology classes. So another way to think about the push forward, if you have a cohomology class on a space, you want to push it forward, it means essentially integrating over the fiber of this map. If you think in terms of differential forms, for example, if you have d something which is dl wedge d tau, or d tau wedge dl, and your space is an R across S1, and you go to R, and this is the ln tau, and you have some function fl tau, so it's a degree 2 form. Pushing forward, it means a differential form not just in L, so what you do is just integrate in tau, and here it's in the right degree to do that, and you use the fact the fiber is compact. So that makes sense to integrate. So it's going to be the integral from 0 to 1 fl tau d tau dl in that case. So here we are working anyway with compact spaces, so the fiber also compact, so this operation of push forward is essentially doing that, taking into account stabilizers, so automorphisms. Okay, so we have this algebra, we want to compute with it, and we have operations on it. We don't have yet interesting classes on it, so that's what now I need to describe. So we need natural classes. So somehow that was the introduction. Now I'm talking about natural classes. Good. So first, there are the psi classes. So psi I. And so the way to get classes, geometrically, if you have bundles, you can take complex bundle, you can take Chern classes. And that gives you geometrically defined elements in this cohomology ring. So a bundle over mgn bar, it means that for any curve with marked points, you want to associate a vector space, or maybe just a complex line for the moment. And then when the curve varies, this vector space is also going to vary, and altogether it should be smoothened out so that it forms a nice holomorph, for example, holomorphic vector bundle. So one thing we can do is we say, okay, we look at the curve, and we look at the cotangent line at the ith marked point. So for a fixed curve with marked point, it's a complex line. And if you were taking another curve, there would be a canonical isomorphism, so it doesn't depend on representative in that sense. And now you vary the curve over the moduli space, and it forms a holomorphic line bundle. So you can take the first Chern class of this. And this will be an element of H2. So what Chern classes are doing, one intuitive way to think about it, I mean, it's for C1, but that works also for CK, that when you have a holomorphic vector bundle, imagine so you have a compact space, take, so let's say with a line bundle, take a section which is generic enough and which is, say, meromorphic, because sometimes there's no global section. Then you look at the locus of zeros and poles of this section. If you take another section, the ratio of two sections is going to be a function. And you can argue it's going to be the same homology class for this locus of zeros and poles with multiplicity. So this locus of zero and pole, it's a divisor. It's something of complex codimension 1. In homology, if you go in cohomology, it becomes something which is of cohomological degree 2. And that's this element of H2. So this is one way to understand what Chern class are meaning. Essentially, they encode loci of the generation of generic enough sections of holomorphic vector bundles. There's other ways to describe them in terms of connections, curvature form, etc. But somehow this is less intuitive than this one, because we're really counting where is it not, for example, where things have zeros. Or if I take two sections, where do they have common zero, where they become not anymore independent. That's what Chern class are essentially doing. And so this is somehow why we're talking about intersection theory. We're going to take certain geometrically defined classes, and we want to know when sections of those degenerate or are not anymore linearly independent, and that will be a certain sublocus. We want to intersect it with another sublocus, which is also interesting, and we compute this, so these are called intersection numbers. So that was for the hand waving about Chern classes. But what we're really going to use, so the main point of this talk is that you need, so there's this kind of algebra, cohomology algebra, with interesting operation on it. You need to know a few facts from geometry, and one fundamental result, which I'm going to quote and which is related to TR. And from that, everything else is algebra. And what I'm going to explain, I mean, there will be almost no proof today. I'm going to explain you once which are these basic facts you need so that you're able to do the algebra. Okay. So then there's the kappa class. So for the kappa class, you're going to take this forgetful map. So I fix Gn. So it's a map going from mgn plus 1 to mgn. And you're going to push forward psi, the one associated to the n plus 1 point, the one you forget along this, to the power m plus 1. It's kappa m, and here I have m plus 1. So kappa m is going to be an element of H2m. So why is it the case? The m plus 1 power of the psi class, so what I mean is really the cup product, or in terms of differential form, there's the wedge. But since they're even degrees, there's no sign to worry about when you take product. So I'm going more or less to forget all the time the cup product, which is what usual product in this algebra. We're never going to see an odd form today. So everything is commutative. Yes?
Can you make the pen a bit thicker?
Then I take another one. Okay. So this guy is of degree 2m plus 2. But then we push forward, and pushing forward, what's the fiber of this map? The dimension here is 3g minus 3 plus n, and here it's 3g minus 3 plus n plus 1, complex. So the fiber is complex dimension 1, so real dimension 2. So when you push forward, you integrate along this fiber, so you lose dimension degree 2. And that's why when you have m plus 1, you get to 2m. Okay. And then there are another important family of classes, the lambda classes. So it's the jth Chern class of E And so here it's called the Hodge bundle. And to introduce it, you should think, if you have a Riemann surface, what is the most natural space that you have attached to it? So here there was some, because you had mark point, but you want to look at the space of holomorphic forms. So if I had a point in MGN, I would just look at, so what is the fiber of E? It's going to be, so what you denote like this global sections of the sheaf of differential, but this is just the space of holomorphic one forms. And somehow it doesn't depend on the puncture. Good. So this is a vector bundle of complex rank G. You have G independent holomorphic forms on the curve of genus G. And it extends to MGN bar. And in fact, even geometrically, it's rather clear what happens, because what is a holomorphic form on a nodal curve? So I want to take again my example. That's why I didn't erase it. So this is an elliptic curve. We should find one non-zero holomorphic form up to scale. And the holomorphic form, it's actually dx. And dx over y is a holomorphic form. So one can check that. This is when the curve is smooth. So what that means is that you have to check when is dx 0. So you have to check, so this dx, okay, is going to be regular, except perhaps when x goes to infinity. But then you have to compare how y behaves. And if you take a good local coordinate near that infinity point, which is going to be, so something like this. So I guess you want y, which is 1 over z cube, x is 1 over z squared, and z is going to be a local coordinate. You express everything in terms of z when z goes to 0, and you're going to find that this is regular. So it's a holomorphic form. So in other words, I can write it like this. It's maybe the way that elliptic integrals come up. I mean, from the 19th century, that you have this square root. So on the P1, which is where the x coordinate, this is multi-valued, but on the elliptic curve, this is a meromorphic form. But what happens when t goes to 1? When t goes to 1, you're going to see dx over, okay, square root of x, but x is close to 1. Because that's where we want to look at x goes to 1, because that's where the node is, and we want to know what happened at the node. And here we see square root of x minus 1 squared, so we see something like this. So we realize that, okay, we have this family of holomorphic forms, and they're still holomorphic, except at the nodes, where the node they start to have a simple pole. So at the node, x is a local coordinate, but you have 2, because you have 2 branches meeting. So you start to have a simple pole, and in fact, what happened is that at a node, here there's a residue, which in that case is going to be some number. On the other side, you have residue minus 1 for orientation reasons. So the right definition of holomorphic form on stable curves, it's one form which is holomorphic everywhere except at the nodes. At the nodes, it should have simple poles with opposite residues. Opposite residues. So the residue on the normalization, the residue here is C, then the residue here must be minus C. And this comes naturally from looking at families of holomorphic form on surfaces that degenerate. Yes. Yeah, there's a decay, a natural decay. So in fact, I want to say that here. So on a stable curve, a holomorphic one form, so by definition, is holomorphic away from nodes and has at most simple poles. It could also be regular at the poles. At most simple poles with opposite residues. At the node. And for that reason, in this elliptic curve case, you see when we pinch that cycle, if I look at the normalization, this becomes a sphere. There's another mark point here. And on the sphere, we know we don't have holomorphic forms. But we do have a meromorphic form with simple pole here opposite to that one here. And with that notion, somehow it preserves the fact that even on a degenerate elliptic curve, there's still genus equal 1 holomorphic form. So when you extend this bundle in this way to the boundary, the rank remains the same, still G. You don't lose anything. And so that can be a vector bundle. And therefore, we can look at Chern classes. And that's an element of H2G. Okay. So now I will start, up till now I tried to explain where everything was coming from. And now I will start to give some basic facts from geometry, which are not too hard, but which I'm also not an expert in doing that super carefully. And in fact, there's been a reference which has already been uploaded for another course, which is the lecture notes of Dimitri Zvonkin on Grothendieck-Riemann, Roch, psi classes, etc. And it's a very nice reference if you want to know a bit more about the proof. I mean, with intuition, with a good intuition, even if you're not an algebraic geometer, of the basic facts I'm going to say. So the basic fact is that what happens to these classes when you push them forward or pull them back? So here this is on MGN plus 1. I can pull the psi class on the MGN. So I use the same notation, but they live on different space. I hope you're not confused, because I don't want to write this each time. So when you pull that back, this is not the same. And the reason why it's not the same is precisely because of this phenomenon that we had to stabilize the curve, so contract unstable component. And so, in fact, there is another class here, which is the cohomology class dual to this locus, where the ith point and n plus 1 point is together in a sphere attached to a node to the rest of the surface. Yes. So I'm not going to explain too much the detail, but again, there's the nice, very nice notes of Zvonkin. But the corollary of this is the string equation, which tell you how to compute. So I don't know, maybe Bertrand talked about the string equation? No? So you haven't seen it before. So when you have an integral over mgn plus 1, and you don't have any psi class here, not attached to the n plus 1 point. So if you want, it's psi n plus 1 to the power 0. Then you can compute that in terms of an integral over mgn only. And the way to do it is to sum over all choice of the one of the endpoints. So you integrate over mgn bar. And then all the psi classes here remain the same, except for one, which is going to be decreased by the power by 1. Okay. So I think the exercise was showing that you will see soon that this is completed by topological recursion. I think the exercise was about proving that type of identity for the omega GNs from the topological recursion. And this is the geometric origin of it. So great. When we don't have side classes, we know how to reduce the complexity of these integrals. The next thing is called the Dilaton equation. So imagine that now I don't have this psi n, but I had rather something like this. I have 1 power of psi n plus 1. So that's almost by definition of these kappa classes, that would be kappa 0. If I want to integrate over the fiber, that will remain unchanged. And I should have here kappa 0. And it turns out that kappa 0, so what is it? It's an element of H0. So the space here is connected, so this is just a number. Multiple of the unit. And what is this number? It's 2g minus 2 plus n. So I write 1 for the generator of the H0 in cohomology. And so what it means that here is the kappa 0 on that space, not on this one. So here, when I integrate over mgn plus 1, I'm going to see that times 2g minus 2 plus n. So don't be confused about putting n plus 1 because there was n plus 1 here. This is the one lower. Okay? And then there's the next fact. So we know what happens with psi to the 0, with psi to the 1. We can forget it. Yes? Where? Here? So the indices, you mean? Yeah. So we want to see what happens when we not only forget one point, we forget many points. So I want to look at FL, which is just repeating several iterations of this forgetful map from mgn plus n to mgn. And you want to look at, so I'm going to maybe first give the property and then the consequence. So one can prove then kappa j, that's on mgn plus, let's see. Yeah. So maybe I want to do that after. First, I give the property. So for the usual f, kappa j on mg n plus 1. If I was putting back the kappa class from mgn, it's not quite a kappa class, but there's a correction which is psi n plus 1 to the j. Because some of these kappa class come from forgetting one point on mgn plus 2. And so there's a bit of interaction about how, in which order you forget this point, and you get an extra term. But the way we're going to use it, so maybe I write that here. Is that if I look at this iterated forgetful map, or I forgot the last L points, so I want to push forward something which is a pullback class, and then psi n1 plus 1 d1 plus 1, psi l plus 1 dl plus 1. Yes? Yes. Any j. The kappa class are indexed by an integer. So it's just a number.
And right-hand side? Left-hand side, now.
So kappa j is equal to the pullback of kappa j on MGN.
Ah, J, sorry. Sorry. It's J everywhere.
Yeah. It's kappa j, and here psi to the power j.
It's my eyes.
Yes, it's my writing too small. That has consequences. Good. So we want to compute that, and why do we want to compute that? Because we want to compute some integrals like that. Maybe you have a class which is a pullback from mg, so that's FL. For example, that could be a combination of psi 1, etc., psi n. And here you have these things. And the kappa class told you how to forget one point. And the question we want to answer here is what happens when you forget several points and there's certain powers of psi classes? Normally you can express that in terms of kappa classes, but there's a bit of combinatorics in doing that precisely because kappa classes have this kind of behavior under pullback. So when you do iterating forgetful maps, you have to be a bit more careful because of that relation. So useful for this. And so what is this? So this is x times the sum of all permutations of L, the product over all cycles of sigma, and the kappa class where here you sum all the di's in this cycle. So if I do an example with F2, that will be x, and you would have some kappa d1, kappa d2 that correspond to the sigma equal the identity. And then you have kappa d1 plus d2. And that corresponds to forgetting psi n plus 1, d1 plus 1, psi n plus 2, d2 plus 1. So you see it is not just a product of kappa classes, there is kind of interaction here. Okay. So that's what we need to know for the moment about these classes. Yes?
Can you write that last formula like in homogeneous polynomials of kappa instead? I mean, I think you sort of did.
Not
I mean, in
quite.
So, sorry, symmetric.
Homogeneous in
I
coverage
mean,
degree.
symmetric in the D's.
Well, I mean, you see your generator in degree 2j, that was kappa j. So this is the formula. I don't have at the moment a much better than that. That's the general thing. However, we'll see a nice way to do that with generating series afterwards. Okay. There are other types of classes which are going to be useful. It's classes coming from the homology class of some boundary strata. So it's great because I have my gluing maps. So this I'm going to erase. So that was maybe A, and I have B for boundary classes. So what is the type of a stable curve? We saw that it's just since component attached to a node, we can encode that in a nice way by a certain combinatorial structure. And looking at the locus of stable curve with that combinatorial structure is going to form a certain cycle. We look at the homology class or the corresponding cohomology class, and that's what we call bi-boundary classes. So if you have a stable curve, you can attach to it what is called a stable graph. So first I'm going to do one example, and then I'm going to give the definition in general. So let's do something sufficiently complicated. Okay, and here I need one mark point. Good. So first you take the normalization, so you detach the nodes. And I want to put a vertex in my graph for each of the smooth components. So there's going to be one vertex coming from here, one vertex coming from here, one from here, and one from here, because we have 4 smooth components. Then some of these things come with marked points. So I want to remember that by saying there are legs. Label here 3 and 4. This one has a leg label 1. This one has a leg label 2. And this one a leg label 5. And then when I remember that I had nodes connecting these guys, and therefore I want to put an edge in the corresponding vertices. And here it was connected like this. There's one thing I forgot, is that here there was a genus, which I didn't take into account, but it's easy. I can just say that this vertex has an extra integer attached to it, which is 1. I call that h. So I will call that the genus of a vertex. Okay. So that's an example of a stable graph.
So
Marta?
did I understand correctly? For every vertex corresponds to a component.
Yes.
Then for every mark point in that component, you put an open edge.
Yes.
Okay.
I'm going to write the list of conditions here. So smooth component correspond to vertices. Marked point on it is going to be a leaf, so vertex V, which is labeled between 1 and n. If there was a genus for this component, you get a genus here for this vertex. It's part of the data of the graph. And then whenever I see a node between, so a node can only be shared by 2 smooth components. That is going to go to an edge. So smooth component represented by vertices V and V prime may be the same. That forms an edge between V and V prime. And now how do we read the genus of the initial surface we started with from this graph? So the genus, total genus of the stable curve, for example, here. So this was, you should imagine that here this was a pinch cycle. So you have one handle here and another handle here. And just a sphere component, so this will have genus 2. So how do I read that here? Well, I look at the number of cycles in my graph and the genus of the vertices. So the total genus G is the sum of the genera at the vertices plus the first Betti number of the graph, which is the number of independent cycles. So stable graph, I denoted gamma in general. So can all these graphs be realized? The answer is no, because we haven't expressed the stability condition, that each smooth component should have negative Euler characteristic. So this explains the name stable here. It means that for any vertex, maybe I write on the right, for any vertex, twice the genus minus 2 plus kV for me is the valency. So including the leaves is positive. And that is a graph which has on top of that a certain genus, a certain non-negative integer at the vertices, which satisfy this condition and this stability condition. It's called a stable graph of type Gn. So I denote Gn, the set of stable graphs. Of type Gn. If now I take such a stable graph, you can look at the locus delta gamma of all stable curves whose stable graph is gamma. So this thing have complex structure. There's a moduli for this complex structure. So what is this? This delta gamma, so I could say, I can write like this. So this is the image of a certain morphism. And what is this morphism? So in terms of complex structure, the smooth components don't talk to each other. There's only a global condition on the total genus. So you just have to say what's the moduli space of complex structure for each of the smooth components. So this is a M, HV, KV. There's a moduli space at each vertex because the vertex is a smooth component. And then you can embed that in MGN bar by saying at each vertex I take a smooth component. Whenever I see an edge, I create a node. That forms a nodal surface. And this is the map I gamma. It's an inclusion inside the boundary of this. You have to be a bit careful. So here I write a bit sloppily because here you have things labeled from 1 to kV. But there is you remember at which vertex there was the leg 1, the leg 2, the leg 3. So in fact, there is a final labeling here. You forget about the label of the thing which are going to be nodes and glued together. But since this is intuitive, I'm not going to introduce a heavier notation for that. And so this delta gamma is called the boundary class. Yes?
Gamma.
It says a closure, it's not just the
Yeah,
image.
because the graph can still degenerate, and I think you want to say that the class includes this
You take
further degeneration, right?
But isn't it included here?
Yeah, no problem there, but just that what you wrote down there in the blackboard, you see you wrote locus of all stable graphs.
Yes, okay, yes.
Curves whose graph is that, or the generation of that.
But wait, I have the impression this is already here. That's include the generations of that.
Yeah. I mean, I agree that when you write image is fine. It's just the sentence that was a little bit misleading.
Okay, yes. Oh, the sentence.
Okay.
Yeah,
Yes,
the sentence, I totally
sentence,
agree.
Yes. The closure of that, yes.
Yes, thank you. Sometimes formula are more precise than words. Okay. Good. So by the way, what's the codimension? Can you tell me what's the codimension of this locus inside MGN bar? Yes. The edges are exactly the cycle that you pinch. And so this is one condition. For example, the t that I had to set it to some value in the elliptic curve example to say that, oh, the cycle degenerates here. You can see as like the length or the period of a certain holomorphic form here is going to vanish. So it's one complex condition, and you have as many as edges to be able to reach that. So as Paolo said, I mean, this actually is further stratified down if you degenerate more, but the dimension of the top stratum of this class is the number of edges. So that in cohomology is going to be in 2. So the cycle has codimension 2e, so the yeah, is going to be like this, number of edges. I think I didn't. Should be okay. Okay.
Just a remark that when the stable graph has automorphism, how do you define the actual
So
locus?
you should include the automorphism. Indeed. So for example, if I do a stable graph like this, so that's a bad example. Let's do something with a loop. Okay, so here you can exchange these two guys. So automorphism of this is going to be, actually you can also exchange these two guys, so I think 1/4. So when you define this class, you have indeed to introduce the factor, as it should. I will actually more work with the I del I gamma, and therefore when I'm going to push forward by I gamma, I'm always going to divide by 1/the automorphism. So it's one situation where it's easier to be precise by words than by formulas. Now the particular case of, particular cases, you can also have the stable graph with one vertex of genus G and all the legs. So that represents actually MGN bar itself. You have no degeneration. If you have just one edge, so you have two types, you have this or the loop. So it's one edge, so it's codimension 1, so it's a class in H2. And so these are corresponding to the locus, I mean the class of a boundary divisor. So divisor is just think of a subvariety of complex codimension 1. So that's in dimension D. So in cohomological degree 0, 2, and then you have lower things. And there's one thing I want to say. So if you have a boundary divisor, so I call it delta is a boundary divisor. That's another basic fact from geometry which I'm not going to justify, but Dimitris Vonkin does it very well, is that in fact when you intersect these homology classes, they do have self-intersection. So if you remember, what does it mean really to intersect homology classes? You take generic enough representative, and then you try to count the number of intersections if this is transverse. And that applies to a certain cycle itself. You take two different generic representatives of a cycle. So if you have something like this, you take another generic one, so it could maybe be like this. And then either it has intersection or it doesn't. In that case, there will be self-intersection. In that case, there wouldn't be any. So when we're going to multiply this class, it's useful to know what is the self-intersection of this thing. And in cohomology, so that can be computed, and this is what I will denote like this. So a boundary divisor is a graph like this. There's one edge. So you have a certain thing here, which is a lag here. And here you have a moduli space. So there's a corresponding psi class because that's a puncture here. So there's a psi class psi bullet and a psi class psi circle attached to these things seen as marked points. And so these are here. And so this thing has self-intersection, which is given by this. So this is a class in the product of the two moduli spaces, and I want to see it as a class in MGN bar, so I need to push it forward to include it in the MGN bar, so that's the inclusion morphism. Yes. Okay. So we're almost finished with geometry. Are there any questions? How are we doing with the time, in fact, Federico? 20 minutes. Okay. Good. So now we have operations on this cohomology ring. We have elementary classes. Let's try to cook new classes out of old one. What we can generate from this structure. So this is part 2. This is operations on classes. And that is not too much related to, I mean, it uses from geometry just what I said, this operation we have, so this kind of structure of modular operand and this forgetful map, and just to have elements. Otherwise, you could do that in more complicated modular operands. Good. So there's two operations related to the two type of morphisms we have. So the first one is using the forgetful map. And I'm going to call it, so the name is rather standard, it's called translation. So the forgetful map FL since we are doing an operation on classes, I need to have a class to start with. So we're going to fix a collection of classes. Could be arbitrary. So translation is going to start with a formal series. And it's going to define a new class. So for each topology, Gn, I'm going to have a new class. And what we're going to do is the sum over all L. We're going to take the class that we have on n plus L. So that's here. And we're going to cup it with what I would denote T hat psi I. So this is a formal series in U. I substitute, instead of using a formal variable U, I replace that by a cohomology class psi I. So I just get a series of powers of psi. And the cohomology ring is nilpotent. So, I mean, at some point you are a dimension too big. So it's going to be 0 in cohomology. So that makes sense to specialize here. So this is now a class on mgn plus L. And I want to bring it back to mgn. And for that, I push forward by this morphism. So that thing I said makes sense because high enough power on psi on a given moduli space is 0 for dimensional reasons. But there's still an infinite sum here. So it may be ill-defined. Because that sum might be infinite, and then I don't know what that means. But if you remember, what's the dimension of this moduli space here? The dimension of mgn plus L is 3g minus 3 plus n plus L. So the problem is that we are growing linearly in L. It wouldn't be much of a problem if here I was having something already of, so let's say dimension over R so that it matched the cohomological degree. So it's going like 2L. So if I was starting here with rather U squared, then I'm saying that this is well defined. Because the first thing that you introduce is a class in H4. I mean, psi is in H2, so the square is in H4, and then you have higher powers. And so you're already eating a dimension 4L, at least. But your space is growing like 2L. So at some point, if you take L big enough for a given term, you're going to have a class, produce a class which has dimension bigger, degree bigger than the dimension of the space. Therefore, this is 0. So the sum becomes finite because of that. Okay, so that's translation. And now we remember we have these other types of morphism, which are the gluing morphisms. Here. And here I must say there's not really a standard name. So I'm going to propose a name which, I mean, I'm very happy if you want to change it. I'm going to call it diffusion for a reason that will come clear. In other contexts, it's called change of polarization, Bogoliubov transformation, but that is not at all enlightening for what I'm doing here. So I prefer to call it diffusion because the reason why I call it that will be clear later. Good. And so for diffusion, so we take a formal series in 2 variables. And I'm going to cook a new class in any topology by summing over all stable graphs of type Gn, here our precious automorphism factor, we're going to pull back and to push forward by this inclusion map into the boundary stratum. So this one here. And then what do we put? Well, it's the natural thing. At the vertices, you have moduli spaces. You're going to put your old class. Omega H V K V. And now on the edges, we're going to put a wave, which is d hat psi h prime. So on this locus here, these half edges coming to a vertex, either it's a leaf for the full surface, so it's a mark point, or it corresponds to a node, a half node. So we have psi classes attached to this, which are the psi h and psi h bar. So this is a well-defined class here. For the same dimensional reason, even though d hat is a formal series that's going to truncate to finitely many powers, I take the product of all of this, and then I bring everything to mgn bar. And so we obtain a new class, which is using the information of omega on topology Gn and all the lower one you get by degeneration. And here we don't have problem. The sum is finite because there's finitely many stable graphs. The stability condition here is important. Yes? Yes, thank you. Yes, very good. Otherwise, I would have problem making sense of that. I would have to be more careful about labelings, which is also possible but not necessary for what we want to do. Okay, so if we have a collection of symmetric classes, we have a way to generate lots of others. And here is an example. An example will actually be, in fact, totally independent of that, but then we're going to recognize an instance of such structure. And the example is from the computation of the Hodge class. So this is another, I would say it's a bit less basic fact from geometry, but this is using standard techniques like Grothendieck, Riemann, Roch to compute the Chern class of this Hodge bundle. There's an explicit and nice formula, which I don't know by heart.